Hey guys, how are you? We're back again with another video. I just want to go over quickly our schedule for the rest of the semester, and it looks like these are going to be our quiz days. And it's right in here from the 22nd on. 22nd, real special day. It's actually my birthday. That we're going to have to really concentrate on chapter 5 because it's really the most important chapter here for you to be successful in Calculus 2. So right here, this last one is going to be worth 50 points rather than 25. So that would give us an even number of tests. And I want to thank you for being so patient and kind. The few of you that I talked with by video yesterday, you're a really great group. I really appreciate it. I really like you guys, and I don't like anybody. But here we go. I'm going to do some examples in section 3.7, which is called related rates. And related rates are, how are things changing based on how other things are changing? Seems kind of strange to say, but I'm going to try to do maybe 4 examples for you, and then you could do the odd ones. And for Caleb, the homework is going to be on page 186, anything from number 11 on. So I'll put it down here in the corner, page 186, 11 on the odd ones. You can do as many as you like. And if you get stuck, just send me an email or maybe we'll chat on Canvas. So number 4 says you have this airplane that's flying toward a radar station. And it's actually 6 miles. It's flying horizontally. It's 6 miles below the radar station. So I drew a picture and I labeled it. And then I wrote down some guidelines that you should follow for each of these problems that might help you to solve them, because some of them do get tricky. So this number 4 is found on page 184. So this is what it says to us. It says that the distance between the radar station down here and the airplane is changing at the amount of 400 miles per hour. And if you could picture this plane coming closer to the radar station, you can see that S is getting smaller. In that case, this would be a negative. If ever you have a distance that's closing or something's getting smaller, a volume is decreasing or whatever, it would always be a negative. They said, what's the speed of the plane then? So if I set this up as x, y, and s, the speed of the plane would be dx dt. And they want to know what is the speed of the plane at the precise time that s is 10 miles, the distance that the radar station is saying the plane is away. And this is what I would do. Number 1, I would identify all the variables that we can and make note of special variables that are constants because they don't change. In this case, y is a constant because that height, the problem tells us, is always going to be 6. It's going to be 6 miles. And then the amount that x is changing is dx dt, so I'm identifying all my variables. The amount of s is changing is ds dt, and the base variable is t. It's not x. We're used to the base variable being x, but in this case, everything relates to time. The miles are changing per hour. So it's a matter of time, so the base variable is time. It's no longer x. The next thing we want to do always is write an equation that relates all of those variables together. All the important ones anyway. And then we want to take the derivative implicitly. And by that I mean when you take a derivative of something like x, the derivative of x is no longer 1, it's 1 dx dt. The derivative of s is ds dt, 1 ds dt. And then you want to substitute any variables that you know and then solve your equation. This one, very simply, we'd use the Pythagorean theorem for the equation, right? Y being the constant as 6. We would take the derivative, so this would be our derivative. I divided both sides by 2 here, and then I substituted everything in there that I knew. Here's the thing is, when they said s is 10, I know because of the Pythagorean theorem x is 8, and you can look at this later or pause your video to think about that. I put an 8 in for x, I put a 10 in for s, and a minus 40 in for the change in the distance between the radar station and the airplane. And I solve the equation, I get a negative 500 miles per hour. And it's not that the plane is going negative fast, it's just that that's the distance is changing and getting smaller, so it's therefore a negative. So I hope that makes sense to you. What you want to look for too is maybe your units. 8 is miles, 10 is miles, this is miles per hour. When you divide the 8 over, you're dividing miles by, this would then be miles squared per hour. If you have a science class, they make a big deal about these units. Math people kind of graze over it sometimes. That one m will cancel out with an m on top, and you just have miles per hour. So number 14 is one of the exercises in the book. And let's look at that one. What it's telling us is that we have the volume of a sphere. And if you ever don't have a formula, you look it up in the back. So we want to write our equation. We want to identify our variables. And number 14 says that, it's this balloon. It's inflated with gas, and it's being inflated at the rate of 800 cubic centimeters per minute. That's cubic centimeters every minute. That's how fast that this gas gets pumped into this balloon. They want us to find out how fast is the radius changing at the particular instance when the radius is 30. How fast is that radius changing at that snapshot in time where the radius is 30? I write the equation. If r is 30, we could put the 30 in there and solve for v. If you want to pause the video and think about how I got that, you can. Take the derivative of this. We multiply the 3 out front. It's funny how the derivative of the volume is, this turns out to be the surface area of the sphere. We could talk about that another time. So, but the derivative of r is dr dt. Then I substitute my variables in and solve for dr dt, and I get 0.071 centimeters per minute. The next problem is 16. And 16 says that all of the edges of the cube are expanding at a rate of 6 centimeters per second, and how fast is the surface area changing at the precise time when the edge is 2. So I drew myself a box. First thing maybe I should have put on that list is to draw a picture. I drew a box where it's a cube, so all the sides are the same. I called them x. The surface area is there's 6 sides to a cube, and each one is x times h, which is x squared. I identified my variables. The x is changing by the amount of 6 centimeters a second. I want to find out how fast the surface area is changing when the side is 2. I take the derivative, I plug in my variables, and I get my answer.